In undergraduate statistics, when we first started, it might have introduced the concept of sample and population. Do we remember that part? Sample, population. Our objective is to understand something about the population. To do that, we get a sample. All of statistical derivations and theory uses that principle. If I pick a parameter, let's say I pick a population, I know the mean of that population is 1.2. I know the standard deviation of that population is 0.4. Yes? If I know the truth, do I need to collect a sample? No, I know the truth. Who cares? I know everything. The purpose of statistics is to infer this using the data that you have. Here is my question. Now, the data is probably going to give us a histogram, something like that. So this is data sample. Mean right over here. Yes? My question to you is that mean going to be equal to 1.2?
Could get close if you have a lot of examples.
Probably not. Agree. It will be a value that is closer to mu if it is a good random sample. No way that it will be exactly 1.2. With me? Theoretically, that is only achievable if you have a sample of size infinity. And we don't have infinity, we approach infinity. Hence that slogan that people use to start, the bigger the sample, the better things are. That's what this is. So I'm going to get a closer value to the truth if I have a larger sample. Going along that logic, expectation of x is the mean. The expected value of the mean that is the truth. That is what I expect to get. Good. So if I collect data and come up with an estimate, same here, I don't have the expected value. Expected value is what I expect to get. I'm going to get an estimate. Going back to undergraduate statistics, what is that notation? X bar. X bar. Throw some calculus in, funny notation. How do we write X bar?
Sum of x of i's over x.
N observations, you're summing all the observations and you are dividing it by n to get x bar. Agreed? What I expect to get, so this is expectation. What I get from the data, reality. Is it going to be exactly equal? No, but something closer. So n observations, summing all the observations, dividing it by n to get an estimate of mu. People often get confused when they see the expectation notation. I want you to think of it in a very informal way. So you can relate it to a sample directly. Can I erase this? No matter what formula you have, anytime you see expectation of x, and you want to connect it to something that is real, say data, this is all you have to do. Everywhere you see expectation, you just replace it by some I equals 1 to n. E becomes that. And x will have an index xi. No matter what expression goes in it. For instance, if I had expectation of x squared, right? This is the truth, this is the theoretical parameter. But if you want to connect it to reality, connect it to data, I'm just going to replace that e by a sum of that sort. Rewrite whatever that I see inside with a subscript like done. Sample case. So I think this is a nice little trick to remember the connection between the parameter and the statistics. Are we clear? Good. Okay. Erase. Okay. Here comes the next bit. Very important. We all know what variance is. Yes. What is variance? Measure of variability. I don't want to get too theoretical. So, COV, any thoughts on what it stands for? Covariance. Why do we call it covariance? Two, you are relating two things. You are relating X to Y. There is a formula for this. I'll mention it here, but as far as this class is concerned, let's not get too deep into this. That is the formula, yes? So the true covariance is this. Things coming back. That's the truth. That is the parameter. That is the unknown parameter. I should probably call it unknown parameter. Let's see if we can use the trick that I suggested and come up with the formula for an estimate of covariance that we can get from that. Just guess.
X I minus mu, y times 1 minus mu.
Yes.
Should it be a double sum or not?
We'll get to that. So, error estimation should be a double sum. It's not a double sum. If we go with this notation directly, let's look at variance for instance. when you find variance, you are looking at x, and you want to see how x is related to x, correct? X to x. So if I simply replace the covariance part, the y by x, covariance xx would simply be the variance of x. Right? If you go back and look at the variance formula, xi minus mu, yi minus, oops, xi minus mu, that's what you would have. Agreed? So if we use the expectation logic, but since we have two variables, x and y, you would have a joint density function. A joint density function would have x and y, in which case you would have a double integral. So direct logic suggests, well, the trick, I gave it to you, you would replace this, but in reality, theoretically speaking, don't worry about the sum. If you put in another variable, you'd end up having another sum. So this would become j. So that part is not that important unless you are a math major. So if you go with my trick, that expectation becomes a sum. But since we have two different variables, we need two different sums. But when I go to the same variable, I have one sum. Good. Well, it's that nice. But here's the catch. We don't know what that is, correct? Do we? We don't know what that is. By all means, that could be different. But I do know how to find an estimate for that. Agreed? Color? Yes. X bar. Y bar. That will give me a sample value. Likewise, if you put X bar here, X bar there, that is the formula for variance. If you go to an undergraduate, go looking at an undergraduate textbook, you will see this formula. Sum I equals 1, xi minus x bar squared. With one tiny catch. Do we remember the talk starts just last semester? No? Why? Okay. There is one catch in this formula. In the denominator, it will be n minus 1, not just n. You may say, well, then, is this wrong? No, that gets into, unbiasedness and other theoretical stuff. Let's not do that. So here it's 1 over n. But the trick that I suggested, where anytime you see E, replace it by a sum. It's a nice way to remember things, but doesn't apply for every single case. Good? So here, you should know there is another sum. There, we may have to adjust it to n minus 1. So, subtle details here and there. So, point number 1, covariance of xy, covariance between two variables. If I have covariance of x onto itself, that would simply become the variance of as properties. So we have covariance, we have variance. Let's say A is some constant. Good. Here's my question. Think before you answer. Zero. Why, Omar? You don't have to memorize these things if you understand. You know.
Well, the variance of two constants will just be zeros.
By definition, a constant is a constant. What does a constant mean? It doesn't vary at all. I'm asking, well, how does the number 2 vary with respect to the number 2? Silly. Doesn't vary, they are equal. Answer is 0. If you take two different constants, how does the number 2, which is fixed, number 4 fixed, how do those things vary with each other? They don't. There is no variability. 0. So AB, AC doesn't matter. Likewise, if B is also a constant, covariance of A, comma B, also 0. I don't want to write linear combination yet today. So what I'm going to do instead is to write the formula for row correlation. If you find the covariance doesn't have a limit. In other words, it can go from negative infinity all the way up to positive infinity. First question, can variance be negative? No, but covariance can be negative. So positive number, negative number, doesn't matter. Here is my question. Does a large covariance between x and y imply a strong correlation between x and y? Let's say you have covariance x, y to the 8092. Does that mean x and y are strongly connected? Related? Yes, no, maybe. The answer is no. So a large covariance value doesn't always imply a strong relationship between two variables. To fix that problem, we have rho, which is the correlation. Rho, covariance of the two, divided by the variance of x multiplied by the variance of y. Standard formula. It's nothing but the standard equation.
I was just gonna say that I don't have this variation, but
Yeah, again, the square root of variance is nothing but standard equation. Good. So that is correlation. In linear regression, simple linear regression, this formula is nothing but formula for linear correlation coefficient. Okay, but what we want is this correlation function. got to start with the covariance function. And then go from there. So covariance. We're moving into time series now. Good. What is the basic notation that we use? X sub t. And we want to know how xt is connected to xt itself. Yes. Xt connected to xt minus 1, xt to xt plus 1, and so on. When we did that picture in R, what was the x-axis? Lag. The lag value, typical notation is h. How is the current x value related to an x value h steps away from the current step? Good. Now, I have to look up the notation in your textbook, but standard notation with gamma. My brain's going ahead of me. So that funky letter is gamma. Gamma of h or gamma sub h, one and the same. Let's stop there. Naturally, if I can get autocorrelation single value from covariance, I can generate autocorrelation function using this. Do you agree? Yes, maybe. So this is where we will start. Just for some thought, think of what the value of gamma sub 0 or gamma of 0 will be. Bring that idea to the next slide. In other words, what is or what does the autocovariance correspond to? Don't forget, this is autocovariance. When h is 0.